Okay, so just to start with some generalities, this is something probably very obvious to all of you, but thermal transport has been a subject of research in many years. And you can see here, this is a number of papers, scientific papers per year. I mean, by searching the word thermal transport in the Web of Science as a function of the year, and you can see that from the 70s all the way to date, the growth, this is log scale, has been exponential. And the interesting thing here is not only to what is somehow obvious for most of us, that is actually chemistry, engineering, physics, and material science, which are the fields which are somehow more related to this, to thermal transport itself, but there's actually lots of different fields which at the end are related to heat management, dissipation, profit from heats in different directions, and so on and so forth. So obviously this brings you to the obvious introduction, that is, why would you like to study thermal transport? This is something that you know. I just go quickly through this, and you know that heat is present in many different processes, industrial processes, chips, and so on and so forth. And in general, the idea is that usually heat is not our friend, let me put it that way. And usually what we try to do is to find strategies to dissipate heat. And this is typically what you find inside a computer. You have a chip, and then you have copper channels, and you dissipate that way. And it's not very complicated to guess already that this is not what you can call a smart approach itself, right? That this is something that looks very basic. And of course, you would like to develop different alternatives to be able to more efficiently or exhaust heat or to reuse heat or to transform heat into green energy of this kind of things. Thermoelectricity actually is a good example of that. I will not say a lot. Claudio was already giving a very nice introduction on that. But at the end, perhaps my approach there is that two keywords that may help in the future to bring new opportunities, which, as I said at the beginning, are profiting for what actually is thermal anisotropy. That is something that is very present in polymers, for example, for all the things that were discussed in the previous presentation, processing, these kind of things. And of course, something that is a little more complicated to discuss here and with few time, that is what is known as coherent heat transport. I will say some words by the end. So without delaying myself too much in this, that as I said, Claudio already explained in detail, thermoelectricity is a very good example on how you can use heat how can you transform heat into energy and just use it to perform any sort of operation that you would like. This was, as Claudio said, it's the seminal paper by Dresselhaus in the 90s, who proposed the idea of the modification of density states and so on and so forth. But from the thermal point of view, when you focus on the freedom of merit that he already explained, one of the strategies that you have is, of course, decreasing the thermal conductivity. And he also shown that by decreasing, for example, in this case, the diameter of nanowires, of course, you induce what is known as boundary scattering. That is, you increase the surface to volume ratio, and so then phonons cannot propagate, or vibrations cannot propagate as efficiently as in the case of bulk. The same you can do in two-dimensional structures. In any way, what I want to show you one more time is that the strategies that you're using here to decrease the thermal conductivity, I'm focusing here on the lattice, not on electronic, of course, this undoped materials in principle, are actually very basic strategies. At the end, what you end up doing here is introducing geometrical scattering, okay? But just introducing surfaces, and so this in some level decreases the effective thermal conductivity or the conductance of this sort of low-dimensional materials to the quasi-2D and nanowires. And again, one more time, of course, it would be desirable to find new ways to do this smartly, in a smarter way. So as I was discussing in the lecture I did online, there are two key aspects, in my opinion, to think when you're thinking on thermal transport. No? And in principle, you think on what is actually the dimensionality of the sample, and I will focus here on bulk thin films and suspended thin films, not nanowires. This is not my specialty. But then it has a key role, and you will see in a couple of slides why, the dimensionality of the heat source. Even if this is a two-dimensional heat source, one-dimensional heat source, or a zero-dimensional heat source. And it will be through the combination of these two things that you will be able, for example, to prove anisotropic thermal transport. Okay, this will come later on the second part of the presentation. So An example we discussed on 2D sources, I mean, the two very simple examples, this is very, very old physics, is the steady state method. This is straightforward. I will just go very quickly here. I explained this already to you guys some months ago. You have a cylindric bar. This is just material. You introduce a temperature gradient. Sorry, you introduce a fixed heat flux. This is basically Fourier law. And you have heat flux is proportional through the thermal conductivity to the temperature gradient. And then you can get the thermal conductivity by measuring the temperature into points and by knowing how much heat you're introducing in one of the sides of the material. And so then you get the thermal conductivity. If the time domain version of this idea of the steady state method is basically the flash method. And in the flash method, let's say the geometrical configuration is very similar, but the difference is that you're heating with a pulsed laser source or a flashed lamp or something that delivers the energy in a very short amount of time. When I say very short, you're speaking probably nanosecond or below nanosecond times. The idea there is that, of course, you will heat on the one side, and with a volumeter, you measure the temperature on the other side. Of course, you need to know the geometry of the samples and these kind of things. And then you have a sort of rise time of the temperature, and the half of the rise time, this thing that you see here can be related. This is the half of the rise time. This is pi, of course. This is the diameter of the sample, and at the end, this is what is known as the thermal diffusivity. Okay, the ratio between the relation between the thermal diffusivity and the conductivity, as also was mentioned before by Claudio, I think, is nothing different from the volumetric heat capacity, as you see actually here. And actually, the origin of this is very simple. It's very simple, and you start from this equation that, from all the things that we will discuss during the presentation, is the master equation, even if it's extremely simple. And this is basically the heat equation in the diffusive limit, what is known as the parabolic heat equation. Here, what you see is a dissipative term, the derivative of the temperature with respect to time, the Laplacian of the temperature. This is the diffusivity, and this basically accounts for the heat source, and this is the heat capacity of the material. Okay. So in the case when you are thinking, am I going too fast, or am I going relatively nice? Decent. Okay, thank you. So then the idea here is that, of course, you have no time component. This is steady state. So this term here is actually zero. This is actually zero. So you end up with this equation only with these two terms that you have written here. And the important thing is that this is, let's say, the easy way to understand why steady state usually brings you to the product of the diffusivity times the heat capacity, which is the thermal conductivity. In other words, from steady state, you get the thermal conductivity. Now we go for the other example. In the other example, basically what you need to consider that, of course, the heat source is localized in time. So this basically you can ignore because during the heat propagation process is off. And at the end, the equation you solve is basically this term equal to zero. That is basically what you have right here. And you see that the dominant physical quantity here is alpha, which is the thermal diffusivity that you see actually here. This is the obvious or very simple explanation based on the heat equation on why one method or the other one brings you to observe one quantity of the other one. These two quantities are, of course, very different. And in one simple word, heat capacity is somehow, in some regards, a very robust quantity, since it's mostly related to the degrees of vibrations that your material can provide, and in that direction, it somehow quantifies how much heat can absorb by different vibrations. The thermal conductivity, on the other hand, is a catastrophic quantity because it basically depends on everything. Depends on material properties, grain boundaries, impurities, crystalline quality, and so on. And you could just kick a temperature. You can't keep on going and going and going. So it makes, in many cases, very difficult the comparison between thermal conductivities between different systems. This is actually a problem in the field from the physics point of view and from the engineering point of view. So when we think now on one-dimensional heat sources, the example that comes to mind is the obvious, and this is something that actually some of you mentioned me or asked me some stuff yesterday, and this is the 3 omega method. The idea here is very simple. I want just to leave you with the main ideas, not with lots of equations or results. And the idea is that this is you have a sample, for example, you have a substrate, and what you do is you deposit here a transducer. This is basically a metallic strip with dimensions of 1 millimeter in length and something like 10 microns in width. And the idea here, well, you see here, this, of course, this can be mounted inside a cryostat. You can change the width of this, and you have a lot of things that you can play with. But the key point here is how this actually works. This is actually very, very, very simple. The idea is that you will inject through the outer part. This is a 4-point probe measure of resistance at the end. You inject current between this and this the pads, and you measure the voltage here. But the key point is that the current that you're injecting is an harmonic current with a very defined frequency, omega. Okay, so then the voltage that you measure, of course, will have exactly the same frequency. This is actually very obvious. The power that you dissipate, you will know that this goes like the product of the voltage times the current, or the square of the second power of the current. And of course, the dissipation will happen at 2 times the frequency. This is obvious. If you put a current with 1 omega, of course, the current does not really care about directions, and then the dissipation would be at twice the frequency, as you actually see here. So then at the end, if you measure the voltage, and that's the key point, between the inner pads, what you have is the current times the resistance. The current, as I said, is an harmonic current with a frequency which is omega, and the resistance, as I said, will follow the power dissipation, obviously, because the resistance depends on the temperature of the sample or the transducer itself. So at the end, if you multiply two harmonic functions with omega and 2 omega, it's very simple maths. You end up with a component that is at 3 omega and one that is at minus 1 omega that you can ignore. But the 3 omega component is that the one that you can relate, and I'm not getting now into all the equations, it doesn't really make sense now, with the thermal conductivity of the sample. Actually, what you end up doing in this sort of measurements is measuring this 3 omega component, okay, that you find here when you're heating, this is very important, the cable, and from there you can calculate the temperature rise on your transducer. And this you can plot as a function of the frequency. We will put some equations later of the frequency, which frequency, the excitation frequency, and you will find that if you use a log scale, the decay of this is linear. And this is beautiful from an experimental physicist because it's very simple to obtain a number, precise number out of this. Why? Because the dependence is linear, and of course, yes. Sorry, it's a question?
What was
the frequency of the voltage is nothing that you impose. It's something that let's say is developed inside sample. It's 3 omega, which is basically exactly it's basically up here is a product of the current, which is an harmonic function with omega, and the resistance, which goes at 2 omega, because the resistance follows the temperature, and the temperature follows the power dissipation, which goes at 2 omega. Okay. So if you multiply 2 harmonic functions, as I was saying, then you get the 2 components, omega plus 2 omega, 3 omega, omega minus 2 omega, minus 1 omega. So this is 3 omega component that you can relate with the real temperature on the transducer, all right? It's clear? Yeah, okay. So basically, as I was saying, this is actually the key interesting thing that was proposed many, many years ago by Cahill. Actually, this is a proposal by Cahill, who is one of the leading researchers in the field in the US. And basically, this linear behavior, it's not working so well, but this linear behavior what also turns you into a situation that now if you don't have a substrate and you put a thin film, and if the thin film is thin enough, then basically what you end up observing is that the response of a sample plus a thin film has just an offset with respect to the substrate. And the physical explanation of that, or the logical explanation of this, arises from the fact we don't have another one with Artur. We don't have more batteries or something for this, no? Yeah, it's not, but this, if not, it's okay, don't worry. And so basically from this temperature rise, you can also get the thermal conductivity of what in this case of a thin film. Okay, in bulk, you get the thermal conductivity from, sorry for that guys, but it's not really working, from the slope of the temperature as a function of the logarithm of the frequency. And in the case when you have a thin film, you get this from the offset. Okay, and the key point that the slope remains unchanged comes from the very easy knowledge that the thickness of the thin films you're working with is much, much lower. That is what is known as the thermal penetration depth. So actually, this cannot introduce any frequency dependence on the system response. Okay, I will come back to this probably in some slides. Yes? Okay. Okay, maybe I continue with this one while I don't have anything, but in any case. Okay, this sets an example on what is actually this thermal penetration depth that I was discussing. The thermal penetration depth at the end is actually determined by the excitation frequency that you're using. I said that you have a strip and you put a current and the current is AC modulated, and then your sample has certain thermal conductivity or diffusivity. And so the thermal wave that will propagate inside will depend on the excitation frequency, of course, and on the thermal properties of the sample. And this is the L parameter that is actually, muchísimas gracias, that you actually, that you actually see here. And this is the penetration depth case with the thermal conductivity, and it's divided by the frequency, okay? You have here 3 examples. This, I think this is silicon. I don't really remember, it's not so important. When you change the frequency between 10 hertz, 100 and 1 kilo, and this is a point source, it doesn't matter, but what you can see, this is actually what I'm trying to discuss as what is actually the thermal penetration depth. And this has a lot of implications when then you want to make a measurement using. Okay, so what the implications are? One more time, the expression for thermal penetration depth is like this. As I said, thermal conductivity divided by heat capacity and basically the frequency you care about. And when you have your transducer, that of course has a finite width, as I said, close to 10 microns or something like this, and this is your bulk sample, for example, depending on the frequency that you're using, you can be in this situation or in this situation, okay? And the difference that between these 2 cases is really, really important. What is important? Well, because here you have a 1-dimensional heat propagation model, which is actually relatively simple to solve. Nevertheless, in this other case, this is a 3-dimensional propagation model, okay? And the magic of the 3 omega method comes basically from, I'm not going through all the mathematics here, but when you solve the temperature response and the transducer, this is relatively complicated. This is a modified Bessel function of the second kind. But in any case, when you bring this to the large penetration, thermal penetration depth level, which means that the waves penetrate much more than the size of your transducer, you end up with this crazy equation that you see here. And what is actually interesting is what I was discussing before. The temperature response will be proportional to the power, to the thermal conductivity, the length of the transducer, geometrical parameters doesn't really matter. But the important thing is this part here. And this is what I said before. And that is that the temperature will be proportional to the logarithm of the frequency. And the slope is what? Is this term here, where you have the thermal conductivity. And this is the idea behind 3 omega for measuring thermal conductivity of substrates themselves. When you go to thin films, you go to higher frequencies, and of course you have this idea here of the flow, and so of course you can get the out-of-plane thermal conductivity very precisely. So step that, I put 3 examples, and I start with this since I think I'm repeating myself too much. So one measurement in the case, this is beta gallium oxide, just not complete. I will come back to this material later. And you see here that the temperature as a function of the frequency is linear, what I was saying before. You feed the slope, and a very simple calculation, you get the thermal conductivity. This is actually very convenient. You can also apply these kind of things when you are working with thick films, very, very thick films, because at the end what you will find is that when you increase the frequency, here you have it in frequency, here is log frec, that doesn't matter. In this direction, you increase the frequency. And of course, when the frequency is really low, you are measuring all the material. When you increase the frequency enough, you will be proving this part, which is a thick film, not a thin film. And basically, when you go a little higher, you will start seeing finite size effects from the transducer. The important thing is that you have a thick film here. Thick means what? Depends on the thermal conductivity of the material, but on the range of many, many microns. And at the end, what you see is that you have a linear regime here, and this linear regime will represent the thermal conductivity of this, what you see here. Now you reduce the size a little more of your film. This is not a thin film, it's a thick film, it's a thin film. And as I said, this cannot introduce any frequency dependence, as you see actually here. This is actually introducing that dependence because it acts as a sort of thermal boundary resistance. And what this creates is that if you measure just a substrate, this is the black curve, you have a linear dependence where the slope is the thermal conductivity of the substrate, sapphire in this case, I think. Not a sapphire, like the sorry. And then when you basically put a thin film in a low frequency range, of course, what you end up having is the shift. And by just this shift, this would be completely an analog to the electrical case. By this offset that you see here, you can very easily obtain the thermal conductivity of the thin film. And this is what people are doing to measure thin films. Thicknesses depends, but under the order of 100 nanometers, this works really good. 200, 300 as well. Then if you go below 20 or 30, things are getting a little more complicated. Anyway, so let me switch a little now to the fundamentals of thermoreflectance. This would be frequency domain or time domain, and we just focus now on frequency domain. And in this particular case, your heat source is 1D. Sorry, it's 0D. Okay? It's just a point. So what is actually the way that this methodology works, and this actually a very famous technique, frequency and even possibly more time domain thermoreflectance that has really been exploited in the last 10 years. And here the idea is that you have a sample and you just focus on exactly the same spot of your sample, 2 lasers. One of these lasers is modulated in frequency, that is in this case a blue laser, where the intensity is an harmonic function. And in the same spot, you put a laser which is basically constant. The intensity is constant in time, okay? So this is what you do. And if you pump enough with the pump laser, what you will create is that the temperature of the surface would start oscillating because you're just injecting power. This is obvious. And the key point there is that if you change periodically the temperature of the surface, what you will be changing is the refractive index of the material, of the absorption refractive index, or whatever you want to say. And this, of course, will change the reflectivity of the sample. And the reflectivity will be changed mostly for the probe beam. Okay, so now the probe beam will not be a constant intensity in time, but then you will start seeing oscillations, as you see here. You have the pump component here, and then you have the probe component. And the interesting thing about this figure here that you see is that they are not synchronized. There's a phase lag between these two of them, okay? This that is written here in time scale. It's a time offset that you can translate very easy to degrees when you're measuring by thinking, by using a Elohim amplifier or thinking in vectors, okay? And it's actually this quantity, the one that will help you to guess or to obtain the thermal diffusivity in this case of the sample, okay? So going straight for that, what you do is to measure this phase lag. As I said, the phase lag is what is the phase lag, or is difference in time between the pump excitation and the probe response, okay? And of course, the information on the sample is inside what is actually this phase lag through the response of the probe. And these are the kind of things that you measure. And of course, you must do this in a relatively broad frequency range, and by making a suitable model, which basically starts from, one more time, the diffusive heat equation, as you see here, as I showed in the beginning. Let me skip a little all these details. I don't think they're so important, but at the end, if you sort out this geometry for which the solution for the single point would be an exponential divided by the position, it doesn't matter. And by using even the matrix formalism that they use in optics and thermal transport and many different fields of science, what you can even do is just to solve what is actually the response of the surface, even in the case that you have a multi-layered system, okay? This gets complicated. You have lots of parameters inside, and of course, it's prone to some errors. But in any case, this is actually possible, and this is typically the way that you work with this method. What you can measure with this? What can you measure with this? Bulk samples, of course, and also thin films, and also you can have access, depending on the frequency range that you use, to what is known as the thermal interface resistance between the thin film and the underlying substrate. So in this regards, in my opinion, it's a quite powerful technique. With time domain thermoreflectance, you can do very similar things, okay? By using a different technical approach. So at the end, let's go to actually, we are more concerned today with this thermal anisotropy, okay? So that I was focusing on how do you measure thermal conductivity without thinking on directionality. And if you start thinking on directionality, well, there are a couple of things to comment. In the first place, if you shall work with a two-dimensional heat source, as we started at the beginning, you will know that the distribution of power here is homogeneous. You have zero gradient here and zero gradient, and so the heat propagation regime will be one-dimensional. What you see here, so basically you have a 2D homogeneous power distribution. As I was saying, you have no in-plane heat flow, but the problem is again the same. You require bulk samples with a very well-defined geometry, and this is nothing that we want to do, at least in my understanding inside this project, or actually not that. It's not that something is people interested in the last year. This has been addressed 60, 70, 80 years ago. So this does not actually seem to be the most interesting alternative. However, when you go to the completely opposite case, and now you work with a 3D heat flow, with a 0D heat flow geometry, this just says focus spot, which is well represented by frequency domain thermoreflectance, time domain, or even by a case of Raman thermometry. The situation is also a little disappointing. One more time, and I think that the reason is a little obvious here. No, I mean you have this single spot. You have propagation in all 3 directions, so you need to solve the 3-dimensional heat equation. You have a Gaussian power distribution within your spot. And of course, this can be used for bulk samples, thin films, or even nanowires. However, it's not clear that by using this kind of approach, you can have access to anisotropy, because by definition, the source is isotropic, okay? If your material were anisotropic, then maybe you could, but this will be based on intensive modeling. And this, of course, unexperimental is something that wants to do, but only if you have no choice. If you work with a one-dimensional heat source, the situation is completely different. And the beauty of this idea is that the temperature gradient along the wire is 0. So you have no heat propagation in this direction. So if you put it in other words, if you use this heat in geometry, you are able to filter one of the directions of the material. Think on a bulk material, no? If you put it like this, there will be no heat transport here. You will only have in this direction and in the perpendicular, and so on and so forth. Even if you work with a two-dimensional material, and if you put a line, you will not have this homogeneous power distribution. You will not have any heat flow in this direction, but this will be only in one direction. It will be one-dimensional heat flow again. So this seems at the end to be an interesting approach for this. So what people have done here, I would like to describe very, very quickly 4 different approaches that were done in the latest years. Of course, I have my preferences. This is obvious. And you will, of course, notice that very quickly. So at the end, the first idea would be, okay, what were the first experiments on this? And people were saying, okay, we start from time or frequency domain or reflectance. We have 2 beams in exactly the same spot. This is actually a very interesting work, which is based on non-using transducer directly exciting the material. And what you can do is to make a lateral scan with a probe. This would be the most obvious approach to this. And this, and I'll come back to this in a minute. In a different perspective, you can also try to modify this Gaussian spot to something different. And again, I'm coming back to this in a minute. And of course, there are 2 other approaches that you can also think on using this line idea, homogeneous line idea, for this idea of blocking heat propagation along the line. So let's give a look one by one. In the beam offset idea, the idea is that you just make a lateral scan, okay? And by the lateral scan and by solving the 3-dimensional diffusive heat equation, you are actually able to obtain the thermal conductivity of the sample in the lateral direction. One more time, this requires a lot of modeling, okay? And again, it's prone to some errors because you need to assume a lot of things. In any case, this works, and you have a nice example in the case, this nice paper from the MIT, I think, since a couple of years ago. And what you see here, the case of bismuth selenide, molybdenum sulfide, and highly oriented pyritic graphite. And you can see that the guys here get with quite decent precision the in-plane and the out-of-plane values, and you see clear. These samples are actually good samples for this because the thermal conductivity in this direction is 100 times smaller or something like this than the in-plane direction, okay? So actually this works, yes, but this has a problem, and that is when you're working with the spot geometry, the spatial dependence of the temperature field is something like this, where this Q is the thermal penetration depth. So the important thing is not the exponential, but it's the fact that this is divided by 1 over the coordinate. And this, what experimentally speaking, what this generates is that you cannot really move away the pump from the probe because you have no signal, okay? How much can you actually focus? Well, this is limited by light diffraction, a couple of microns, 1 micron, 2 microns, or even half a micron, something like this. And what would be the maximum offsets that you can get? 5, 6 is not much. So all the results that you will obtain here will be probably poisoned by the geometry influenced, sorry for the word, by the geometry of your heat source. So this actually does not seem to be, at least in my opinion, the smartest approach for this. Some years later, or in the same year, a group came with an idea of modifying the shape of the spot. And actually, this is a smart idea, I think, and saying, why are we working with a Gaussian spot? Let's use an ellipse. Okay, an ellipse, of course, will be sensitive to directions because it's intrinsically non-homogeneous. And this is what they did. The material here is irrelevant. I will say some words, but it's not the main point. This can be applied to basically whatever. And here what they are using is 2 cylindrical lenses to change the spot of a Gaussian beam. And this is the way it looks. And then basically the guys were just turning around the sample or the spot, I don't remember, in order to obtain this maps of thermal conductivity here. The real measurements are only the dark points, and the other one, the open ones, are just actually reflections. And they have shown that it's possible to reconstruct, and this is actually very beautiful, the full 3D thermal conductivity tensor for the material. It is something that there's not a lot of work out there where people can show this kind of things. This material is complicated. You will see this, the thermal conductivity tensor, and you will very easily realize this is not a cubic material. You have two off-diagonal components. At the end, this arises from the fact that the material is monoclinic. Okay, I'm not getting into all the details there. Some later. So after this, there's possibly another approach, which I like a little more, which is based on the 3-omega method, coming back to 10 minutes before. And here the idea is very simple. It's just you put one resistor in front of the other one, and with one of them you hit, and with the other one, and with the facing one, or the next one, you measure the temperature. Okay? So the equations for the temperature dependence and spatial dependence of the temperature field are relatively simple to solve here. So basically, by convoluting with the size of the heater and thermometer, you're able to here plot the 2-omega signal as a function of the frequency. Okay, this is not a 3-omega experiment because actually the heater and the thermometer are not the same, but they're splitted. So actually, the signal, if this would be the heater, the signal that you measure here, it's actually the 2-omega signal, which is created by the power dissipation. But it's just a detail. But one more time, here what you do is exactly the same idea. You put a splitting and you try to see what is actually going on from one side to the other. So the fourth one is actually that we have developed here with Mariano 1 year ago. And this is an idea that we quite like a lot. I will speak a little more on this, mostly because I like it. And the idea is based on 3-omega again. But the question there was, the question we asked ourselves is there any way that we can improve this 3-omega idea? And the answer to that is yes. The first problem with the 3-omega method that you have is that it's a contact method. This means you need to deposit a transducer, you need to make contacts, and this is actually not very convenient. If you work with light, you don't have that problem. First advantage. Second advantage, you're working with materials that in some cases, they are electrically conductive, okay? If a material is electrically conductive and you put a transducer, you will have current leakage, and then you have no experiment what to do, okay? So you need an extra step to work on isolation between a transducer and the thin film substrate or whatever you want, and this in some cases can be complicated. When you're using light, one more time, you do not have this problem. And the third advantage, I will say it later. Okay, so basically the idea there is here you see, this is the schematics of the setup, and probably let me ignore this because it doesn't really make sense to get in all these technical details. But the important thing is that here you have the temperature rise. Okay, here you have the two of them are splitted, but we work in a collinear configuration. One is over the other one, the blue is pump, and the green is the probe beam. And here you have the temperature, and the frequency. And you see here that for the case of glass, you have this sort of dependence. And as I told you many times that the dependence should be linear, well, this depends on the thermal conductivity of the sample. And in materials with low thermal conductivity, as the case of glass, the linear regime basically starts a little below here. And then you have this deformation that comes from the geometry of the transducer that you have, okay? But if you go here and you fit this here with the linear curve, then you get perfectly the thermal conductivity of the sample. In the case of silicon, this is the blue curve here. You have a much larger thermal penetration depth. This means much larger than the dimensions of your transducer. Then the response is linear. From this slope, you get the thermal conductivity. And if you've now put a thin film, in this case, 285 nanometers of silicon oxide, then you have an offset. And from the offset, one more time, you can get very easily the thermal conductivity in the same fashion that I was describing actually before. But things, let me skip that and let me go straight to the point. But things get a little more interesting when you go to experiments, and then you will see this is actually the same figure that I was showing just before. And this is what you see. These are experimental measurements, and you clearly see that things are working quite nicely. This is very easy mathematics. It's no surprise at all. This is glass that you see have the same response, and in this case, it's silicon oxide, and one germanium sample. And actually, you clearly see here that between silicon and germanium, the only difference is the slope that arises from a different thermal conductivity. Okay, but again, we're speaking about anisotropy, and what so far, again, I was speaking about the determination of thermal conductivity, and so the question is, What advantage has this method we developed has to measure anisotropy? Well, the idea is that you are working with this line, and the sample is here, and of course, they are not connected. So the idea of rotating the heat source or the sample, it's obvious. So basically, you have access to an infinite number of angles within the surface of a material. And so self-consistently, you can determine the in-plane distribution of thermal conductivity, and what is actually more important and more precise is that you can determine the anisotropy factor in the case of orthorhombic materials or cubic materials, okay? Here you see an example for a material that from the anisotropy point of view, it's not so nice, not so nice, it's just, no, it's actually not symmetric, let me put it that way. This is gallium oxide, it has a monoclinic structure where you have, this means that you don't have 90 degrees between all the angles, but in this particular case, between the A and C, if I recall correctly, yeah, axis, you have 104 degrees instead of 90, and this complicates a little the analysis of the tensors. This is not, yes? No, actually, this is only, the sample is only mounted on a rotation stage. Okay. Commercial rotation, it's nothing fancy. Yeah, actually, what we do for technical reasons, I can comment later, is we fix the heat source on the probe, and what we do is rotating the sample. That's it. And for each angle, we measure the response. And yeah, so what we did here, very simply, the results, again, is very obvious. You see here 3 different planes, which are the A plane, the B plane, and the C plane, and you can see here the blue. This is completely untreated data. This is what comes out from the computer. You have here the B plane, the A plane, and the C plane, and you can see that the 3 planes are highly anisotropic, with ratios that go from 50%, 20% to 15%, of course. And the good thing is that, again, one more time, you can measure as many angles as you want. Okay, here actually you see the fits with ellipses. Actually, the real response of this is not an ellipse, but it's more like a flower in the case that the thermal conductivity is really low. Here, this is just a guide to the eye. And this is actually something that at least in the last couple of 6 months have been rendering quite interesting results within the group with Marianne. So one more thing I'd like to comment on this is that the technique is actually very robust. Okay, we were also testing to what extent we can apply this to, let's say, not so tidy systems as a polished semiconductor with optical quality and all these kind of things. And this, in the case you have just a SPED substrate, and you know this usually have orientation due to the fabrication process. And what you measure here, of course, is way more noisy because you have all these bubbles and imperfections in the surface. This is clear, but still you are able to find this anisotropy. This is actually in line with the optical anisotropy, optical axis that you find in the material. A similar results we have recently produced for very special samples produced by Ana Larromain, one of the researchers at the ICMAB. And these are basically, sorry, you cannot see very well there, but these are aligned nanocellulose fibers, okay? And what we have done there is, again, producing this kind of maps. And of course, the result is a little obvious, but measuring this is not so simple. And that is in the direction of the fibers. You have a thermal conductivity that it can be as twice as large, or 1.8, 1.7, as compared to the perpendicular direction when you have very poor coupling, at least from the thermal point of view. So what is actually quite interesting and nice is that the method is relatively versatile and flexible, which will not be the case when you are speaking with an electrical method, because if you put a transducer and a transducer and the surface is rough, then you will have, of course, no conduction of electricity. This is very well. So with that, I'm not sure if I'm super late already or I'm fine with time, or I can speak some more minutes. Yeah, I can. 5 more? Okay, I can make it. Okay, so to finish, I'd like to show you an example, which is really state of the art in my opinion, and this is something I quite like a lot. And my objective with showing this to you is that actually we were speaking about the geometry of the heat sources in order to study anisotropy, and you can even get more complicated in that direction, okay? I was discussing this idea of the line or whatever, but you will see here that some very interesting experiments where if the shape of the heat source is more complex, you can even have access to different phenomena, as, for example, wave-like heat transport that I will comment very quickly in a couple of slides. So without getting into details, as we were saying, we usually are in what is actually the diffusive regime. And this is the differential equation, which basically, the macroscopic differential equation, which actually governs the evolution of the temperature field. On the other hand, you have ballistic transport, but I will not discuss on ballistic. But the idea, said this a little untidy, is that between diffusive and ballistic, in some materials, there was an effect that was observed in the 60s, first time in helium, and then in sodium fluoride and bismuth, bulk, all of them, which is wave-like propagation, okay? And the idea there is a little that you start with ballistic, phonons or vibrations propagate freely, and at some point they start speaking with each other and changing momentum, but conserving momentum, okay? Which means with no UNCLA processes. And I'm not going to get so detailed on that, I'm sorry for that, but I don't have the time. So at the end, this regime, this wave-like regime, at the end, and after some time, ends up very quickly decaying into the diffusive regime, okay? So the question is, how do you actually see this kind of regimes, okay? And this is actually related to anisotropy in the case of graphite, as I will say. A couple of years ago appeared a paper in Science when people were studying systematically graphene, and all of you, I guess you're super aware of this, and you may even recall that the first time thermoconductivity of graphene, this was close to 2010, by Balandin was by Raman thermometry, and there was a lot of discussion if these results were good or not. And what people have found with years, and for example, in this particular case, they were studying graphite, group in Japan, as a function of the thickness and the thermoconductivity temperature dependence. This is a different approach. And what is interesting about this work is that they also found this different values for the thermoconductivity of graphene when you approach the zero thickness case, okay? And one of the proposals there, which was based in the work that I already described to finish in the next slide, was that one of the possibilities which can explain the dispersion in the thermoconductivity of graphene, not the value, but the dispersion between different experiments, is the existence of wave-like heat transfer. You may recall that in the case of graphene, you have thermoconductivities that go all the way up to 1 or 2,000 watt-meter Kelvin, and one of the initial explanations there was, you may remember that you have this set A out of phonon modes, which are due to the two-dimensional nature, and these modes have a quadratic dispersion, which means low propagation speed, but very high density of states. This is one of the mechanisms that actually was thought to be one of the main candidates, and very recently, a couple of months ago or 1 year, the idea of wave-like transport has been applied to this. So what is actually what I'm speaking about here? Well, one more time, I'm focusing from the point of view of a complex heat source. The idea of this experiment is simple. You have your sample here, you have two lasers. One laser goes from the middle, and it's what you will call the pump laser. You split it in two, and you make the laser interfere with itself, okay? If you make the laser interfere with itself, you will end up here with a sort of diffraction pattern on the laser, okay, with maximums and minima of intensity. And this will, of course, create a local temperature gradient, okay? If in exactly the same spot, you also put a probe beam, please ignore the upper one, just as technical for reference reasons. If you put a probe beam here, what will happen if you have a grating? Okay, when I said grating, I said a temperature grating, but please remember a temperature grating means a refractive index grating. If you have a refractive index grating, of course, you will have diffraction of this probe beam in a different direction. So in these experiments, what you do is you measure the lifetime of this component after the pump beam has heated up the sample in the center. So you have the boom, this has been hit, and then you have some signal here, and this signal decays. Super simple, okay? And the key point idea is, do you have actually a simple heat source in terms of geometry? No. What you end up having, this is just schematics, on the sample is something like this. You have a grating. And if you change the angle between the two pump beams, what you end up doing is changing the splitting between this grating. And so this means the distance that heat needs to travel from here to here to cancellate the temperature gradient that you were creating between maximum and minimum, okay? In this particular case, this was shown in a very anisotropic material that in this case is highly oriented pyrolytic graphite. Again, the thermal conductivity in plane, it's 10 or 20, no, sorry, it's 1,000 or 2,000 or 1,000, something like that, watt-meter Kelvin, and in the perpendicular direction is close to 10, 20, 30, something like that. So you can somehow assume that the heat propagation in this material is actually in plane. But when you combine this with this idea of having this sort of very smart heat source or heat landscape, let me call it like that, you can very efficiently prove what happens in plane. And of course, this is anisotropic by definition. So the results that the guys were finding there, this is, again, graphite, 300 Kelvin. This is the amplitude of this diffracted beam. And this is time. And the idea is that from the decay time, you will get the thermal effusivity. Okay? At 300 Kelvin, you do this by changing the separation between maximas and minima. And what you actually find is that this has a systematic behavior that you can explain very easily with a diffusive model. No surprise there, expected. You decrease the temperature to 80 Kelvin, and the response changes dramatically. When you go to really large lattice, really large, no, I mean like 13 microns spacing between the maxima, this is actually what you see. This is a decay which is monotonous, monotonous, monotonous. And at some point, the response is not like that anymore. And when you start seeing is these oscillations that you see here on the temperature field. And this, to start with, is a signature of the observation of thermal waves in the material. The beauty is that, of course, you can come up now with the Fourier transform of this, and then you will get very sharp peaks between 100 megahertz and 1 gigahertz, depending, of course, on the lattice spacing that you know. And this is possibly it's a very recent paper, and it's possibly one of the strongest demonstrations of the observation of these effects at relatively high temperatures, let me put it that way. With that, I would like to conclude with an experiment from yours that I like a lot. And if I'm saying nonsense, you please stop me, okay? But there's one thing that I like very much for what you guys have done there. Claudio and colleagues basically have a thought on the idea of well, they published a very recent paper when they were studying this cumulin chain, which is basically a chain of carbon atoms finished by hydrogens, and they were reproducing exactly the same experiment I was just saying, and the result is actually very inspiring to me, because if we go directly to the point here, you can see here the Fourier transform of the time trace, and you can see here low temperatures, room temperature, and high temperatures, and the interesting result is that whenever you see a peak, this means, of course, that you have a wave propagating. And actually, you'll see that in almost all the figures, you do see a peak. Okay, so at the end, to my understanding, please correct me if I say it wrong, but what they're showing is that there are always some sort of situation, experimental situations, where you can observe this effect. Of course, when you go to really high temperatures, well, the lattice spacing that you will have to work is extremely small, and this is nothing that we experimentally can do. Okay, this actually did happen already. At room temperature, I'm not even so sure. And this actually, it's a little more complicated. And to finish, one more figure produced also by the guys here, which is very nice. And if one is critical, no, and you say, okay, what is the definite proof that you have waves there? Only these oscillations. What is that? That's not good. Okay, so what they did is a very beautiful figure for me, and they were basically putting here. You see, this is the initial thermal landscape, and then in this direction, time starts elapsing. No? After some time, you have a decrease of this, and close to 30 picoseconds, you have no more signal whatsoever. Okay, the temperature is stable. But what is surprising is that something like 50 picoseconds or something like that, or 60 after, you have a rebuild of the temperature landscape, but with a phase shift of pi that you can very clearly see here, from here to here. Okay, and this for me, and I think also for you, is that correct? Yes, I guess. Okay, this is a very clear demonstration that the wave, the heat transport regime that you are seeing there, it's dominated by waves and not by diffuser or by diffusive or actually ballistic transport. And with that, I would like to finish. I will not make conclusions because I think the presentation is too scattered. As conclusion, I would like only to say the two things that I said at the beginning, and that is that, in my opinion, there are two main directions which we should, or at least I think, that should be studied in the near future, which is anisotropy and of course coherent effects. And from these two directions, I'm quite sure that we will be able to make nice and different and new experiments in the field of thermal transport. Thanks.
Thank you, Sebas. Questions? One naive question. The light source you use to heat up the system, when you have this elliptic shape of your light, I was wondering, can you also play with the light polarization or not?
I didn't hear the second part. About the?
I was wondering if you can also play with the light polarization.
With the light polarization, you're saying there.
Because if okay.
You don't use transducer, possibly yes. And this actually has to do with the same reaction. Well, of course, you have a polarization. But on the material,
because I thought that you could change the orientation of your polarization of the light and not the orientation of your. I don't know if you understand what I mean. Actually,
yes,
you have a beam that is not.
You're saying for making a 360 degrees map, right?
Yeah.
That's what you mean.
Yeah.
Well, but I think that this is most related to this, I guess. Oh, sorry. Back. Ouch. Okay, to this, I guess, but in this particular case, is again the same problem. You haven't a transducer there. But what we're saying is perfectly valid. If you would have yes, this could work. Why not? Why not? But no, but still no. But still no, because sorry, no, still no, because you're fixing the direction of the heat source with respect to the axis of the material, which means that no heat flow will occur in that direction. Done. So that direction you don't see. You're working now with a 2D material. It's really like that, which means this direction and the perpendicular. So if you want to have access to a different, even if you change the polarization, you will change the absorption, the amount of absorbed power on the material. This is correct. Yes, I agree with that. But if you want to have access to the perpendicular, you need to rotate something. That you can do electrically, yes, of course. But if you want to do this electrically, imagine you need to fabricate infinite numbers of samples. In this case, you don't. With one sample.
Thank you. Thank you very much for this fantastic talk. I have a question about 3-omega method.
Yeah.
If I understand correctly, we need to deposit a sensor on the sample when we use a common 3-omega method. Yeah. So if we can use 3-omega method to measure the thermal conductivity of some electrical conductive material, if when we apply the voltage, electricity into the sensor, if the sample is conductive, is electrical conductive, the electricity will go into the sample. So how to?
You can. The typical approach to do this is to insulate the sample. I'll give you an example: silicon. Non-intrinsically doped silicon. Typical substrates, they conduct quite a lot, actually. Okay. How do you measure this? Well, actually, what you need to do is to grow a thick layer, for example, of silicon oxide over the sample. Okay? But then you start with problems which are related to processing, which is you have a surface. If the surface is not super clean and you put an insulator, you have dust or small part if you don't do this in a clean room. And so then when you insulate this and you put a transducer, you will have still channels where you conduct. Actually, the way to do this is if you still have to do this, you get your sample, you put an insulator, you put a transducer, and then you spend some time checking for leakages between the transducer and the substrate. That is the way. And this only works if the substrate is conducting. Because if the substrate is insulating, there's no way to fix it because the current can go through the thin film. And then there's nothing you can do because you cannot see it.
Yes.
I mean, the 3 omega method, when the sample is conductive, it works, but from the experimental point of view, it gets tedious.
I see.
At least in my experience, maybe there's people who can do this much better, right? Not in my case.
Some other question here on the ESR side? You have one?
Yeah, for the analogous of the 3 omega method with elliptical light.
Yes, but it's not 3 omega.
It's not 3 omega. Okay.
No, actually, I'm sorry if I was going too fast. You mentioned this, right?
Yep.
No, there the detection mechanism is time domain thermoreflectance.
All right.
Or frequency domain, if you want. I should say.
Okay.
They do time domain, but not frequency. And the idea is just deforming the. Sorry. Tell me.
No. Yeah, I think that my question might still hold. Like you said that you showed for the PET measurement that still the surface roughness, it's not a huge problem. But I was wondering if in quantitatively to measure the real thermal conductance, if the model that you assume also are affected by the roughness and this kind of, or if it.
Okay. No, actually, in the models, you don't assume any sort of roughness. No,
okay.
You don't. I mean, you're speaking about this, I guess, or
yes,
this kind of things.
Yes.
No, you don't assume the roughness.
Okay.
This would be super complicated. I mean, I wouldn't even know how to really quantify all this there. It's very complicated in the same position. And then even introducing this, it's difficult. My point here is that the approaches that I'm trying to show are the ones when you can get results from fitting a straight line. Done. Of course, you can do much more complicated things. This is easy, doing complicated things for me. The difficult thing is the other way. It's measuring things that then you can get values with very, 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 very simple model.
Okay, so
because why? Because at the end you get more accurate results.
So in this case, like the main aim is to show that there is actually, you can actually see the anisotropy or even quantify the anisotropy.
The first one is that you said.
Okay.
That with this method, since it's optical and whatever, you can still measure this kind of things. Yeah, the quality is the quality you see there. Of course, you can complain about that, and I would complain with you because if you compare this with this, it's a completely different thing. No.
Yeah.
Completely different thing. But still, you can get an estimation for the anisotropy in this kind of systems, which are nothing that you've probably prepared high-tech lab and this kind of thing.
No, I think it's very cool.
For example, for the industry.
Yeah. Thanks.
To you.
Okay. If there are no other urgent questions, and if there are, I mean, Sebastian will stick around. Maybe you can thank him for the presentation.
Thanks.